Hello all. Today I'll be discussing with you the topic of electron optics, i.e. how electromagnetic lenses work, also known as what forms your image in a transmission electron microscope. To begin, let's discuss how optical lenses work. Lenses that focus light, like the ones you wear on your face, are simply curved pieces of glass. The light traveling through this curved piece of glass is refracted, which means that it slows down because it has entered a medium different than air. Think about how you slow down when running if you run from air to water. It slows down to a different degree depending upon the angle of incidence through the glass. And through slowing down, it changes direction. Eventually, the light rays are focused to a point. In TEM, we use electromagnetic lenses because electrons can't be focused with glass, but they are charged particles, so we can alter their paths with a magnet. And their strengths are adjusted not by curving them greater, as with a glass lens, but by simply changing the current running through the electromagnet. Next, let's discuss briefly how a TEM works so that we understand the absolutely crucial job the electromagnetic lenses perform. In TEM, we have a gun, which is usually either a thermionic source or a field emission gun. A thermionic source basically heats up a filament until enough energy is provided for electrons to be kicked out of the material, much like a light bulb. Then electric fields guide those electrons toward the optic axis of the instrument. In more advanced TEMs, we use field emission guns, so I'll briefly describe those. A field emission gun has an extremely sharp tip which confines the electric field in that area, making it much easier to extract electrons. A voltage is applied to the tip to extract the electrons, and another potential is applied to accelerate those electrons along the optic axis. Now that we've discussed the gun, at this point, the electron beam is condensed, because if left unchecked, the electrons would go every which way. We do this using an aptly named condenser lens. Next comes an aperture, which is a fancy word for disc which allows only well-condensed electrons through, and bad electrons don't make it to the sample. Next, the beam hits the specimen, where the electrons are scattered every which way. An objective lens then focuses the electrons back along the optic axis, with only well-behaved electrons making it through the objective aperture. Finally, the electrons continue through a series of lenses, making it through the last projector lens to the imaging screen. As you can see, what really runs a TEM are the electromagnetic lenses. From the top, they look just like donuts, with copper wires and water cooling pipes surrounding them. And if you cut them in half and look at them from the side, they have many turns of a copper coil encased by a soft iron pole piece. An electric field running in a coil produces a magnetic field with a direction dictated by the right-hand rule from physics. Basically, curl your right hand around the turn of the wire and your thumb will point in the direction of the magnetic field. In this case, we have a uniform BZ pointing down directly along the optic axis. But recall that magnets actually have field lines, like this. So we actually have a non-uniform magnetic field in the plane of the lens called a radial magnetic field, BR. At this point, it is useful to describe a coordinate system. The beam and lens form a cylinder, so let's name our coordinate system cylindrical coordinates. Z will be this way, R this way, and theta as the angle. RBZ in this direction along the cylinder, and our BR in the plane of the cylinder. So for example, if an electron is coming perfectly on the optic axis, it never encounters this radial magnetic field BR and simply passes straight through the lens without changing direction at all. This is analogous to the optic ray passing through the middle of an optical lens. Let's consider the case in which an electron comes in off-axis. When the electron comes in off-axis, it encounters this radial magnetic field. The first thing this radial field does is give the electron some angular velocity, beginning to curve the electron's path. As the electron continues on its angular trajectory, it nears the optic axis. As the electron continues to the center of the lens, the angular velocity encounters the Z field, which produces a radial force pushing the electrons toward the center of the lens, like so. It actually does a little loop around the optic axis as a result of the angular and radial velocity. As the electron leaves the center of the lens, it first loses its radial velocity, then its angular velocity, but picks back up linear velocity and is on a trajectory to reach a central focal point. The more off-axis an electron is, the more dramatic this process. Any imperfections in the magnetic field of the coil can be fixed with an additional magnetic field below the lens, which can nudge the beam to become circular again. This is called sigmation. And at the end you have a nice circular beam. Electromagnetic lenses are powerful tools and are the meat of what produces your images in a TEM. Many improvements have been made to them over the years to counteract any imperfections.